Many concepts in modern technology are inspired by natural processes. Some connections between nature and technology are more obvious than others. For example, Japanese train fronts were inspired by birds. The resulting design reduced noise and energy consumption significantly. Other connections are less obvious. A glowing piece of metal couldn't help us find a path for a rover driving on another planet. Can it though? Obviously it can, otherwise I wouldn't tell you this. The concept I'm talking about is called simulated annealing and is the topic of this video. So let's get back to our glowing piece of metal. What is actually happening here? In materials science, this is called annealing. Basically, annealing is a process of cooling down. When the metal is at high temperature, atoms can overcome the forces holding them in place. Thus, the atoms can move. By glowing, metal releases its energy and molecules slow down their movement. When this is done slowly, the atoms end up forming crystal structures. The results differ depending on the time taken for cooling down. Cooling down fast leads to less optimal states, but cooling down slow forms near perfectly ordered structures. By doing this, different properties of the metal can be achieved. Simulated annealing, on the other hand, is an optimization technique. As the name says, it simulates the process of annealing for optimization problems. This is usually used when simple algorithms get stuck in local minima or when the problem is too complex and it's impossible to compute an exact result. So simulated annealing is an approximation algorithm which does not guarantee to find the best solution, but usually performs well. In simulated annealing, high temperature means that our algorithm is exploring and also considers worse solutions. At low temperature, it only accepts better solutions. Let's take a look at an example. Initially, we have to randomly guess a solution. So this is our current best guess as a solution in optimizing this cost function, which is the global minimum here and the local minimum here. We have to overcome this barrier here so that we end up in the global minimum. So to get a better solution than our current best guess, we could apply algorithms like gradient descent or the hill climbing algorithm. But these algorithms have one common problem. They cannot overcome local minima, as you can see in this demonstration. So if I start this, we will simply get stuck here in the local minimum. Simulated annealing, on the other hand, can overcome these local minima. So let's apply simulated annealing here step by step. The first step in each iteration is randomly generating a neighboring solution. For this simple optimization problem, we can define a step size, and then we randomly move to the left or to the right by this step size here. So yeah, in all directions here. So let's start this. And as you can see, we will just generate random solutions. But this doesn't help us yet to find a good solution. The main idea of simulated annealing is that we also accept worse solutions, but over time we tend to accept less of those worse solutions and mainly better ones. This is done by introducing a temperature. Initially, this is set to 10 right now, so it's so high that we accept nearly all solutions. If we reduce this temperature really quickly, we will accept less worse solutions and we'll get stuck here in the local minimum. This happens because I quickly decreased the temperature when we were close to the local minimum. So we have to do this slowly. And the idea is then that at some point here, the temperature will go down to a point where we can still overpass this local minimum, here this barrier from the right side. But when we are at the left side, we have a hard time climbing up here because it's really steep. So if we do this slow enough, we will basically end up in our global minimum. So when we generate a neighboring solution, we first have to compare the cost to decide whether we accept the solution or if we reject it. If the cost of the new solution is lower, we always accept it. If it's higher, we use an acceptance probability, which we can model as an exponential function, which you can see here. As we only compute this probability if the new cost is larger than the current cost, the numerator is negative, and thus the result will be a number between 0 and 1, which we can use as a probability. The temperature in the denominator is basically a scaling factor. High temperatures will lead to a high acceptance probability because a high temperature makes the argument of the exponential function go closer to 0. Thus, we have a high probability. Low temperatures, on the other hand, lead to low acceptance probabilities. So when we do this on Mars, for example, on a rover, we obviously do not want to cool down the temperature ourselves. So we want to do this in an automatic fashion. This is why we introduce a cooling factor, which is the most common way to cool down in simulated annealing. So the cooling factor is just a factor by which we reduce the temperature in each iteration. So let's just run this whole algorithm again, and this time with an automatic cooling implemented. So as you can see, we'll quickly reduce the temperature, and here we can still overcome, here we can see climb here quite a bit, so we can still overcome this minimum here. And yeah, if we cool down slow, we will usually end up on the left side. Here this is not that stable because the visualization needs a lot of time, but most of the time we will end up at the global minimum. There are many different cooling schedules. For example, there is logarithmic cooling, which is really slow, but also more complex schedules like a mixture of both, like the one we currently use, and logarithmic cooling, but also some strategies at which we reheat the system so when we notice we get stuck, we add some heat and try to escape again where we currently are. Yeah, so as we can see, we found a pretty stable solution. Usually you would randomly select the step size, but right now we could just also reduce it by hand really low. So we would find a pretty good solution when we are at a temperature of 0. So a temperature of 0 is a special case. There we simply take the best solution. We do not accept worst states there anymore. So let's get back to our slides and take a look at what we've actually done here in terms of pseudocode. Initially, we generated a random solution, so just as a first guess. Then we started iterating, and we obviously need some termination criterion. This will not be discussed in detail in this video, but you could make it dependent on the temperature. You could say until we converged. You could also average over the acceptance probabilities, and when this is basically 0, you terminate. Yeah, but this will not be discussed in detail. Then in each iteration, we generated a neighboring solution. So in our case, by just going left or going right a little bit. And then we just accept the new solution if it's better. So we always accept it then. And if it is worse, we compute an acceptance probability and just accept our new solution with this probability. In the end, we have to also update our temperature, so we decrease it in each iteration. The result will be an approximation of the global minimum, so it might not be optimal, but it is usually a good guess if we have chosen good hyperparameters and if our concept is suitable for our problem. So generally, this code, this pseudocode is rather short and it looks rather simple, but obviously there's a lot of work behind these steps here, especially when we have more complex problems. So yeah, like generating a neighboring solution is usually not just going to the left or going to the right. It can be far more complex than it is here, but we'll take a look at this later on. Applying simulated annealing for path planning can be done in several ways. You could either design your own algorithm, which is completely based on simulated annealing, but you could also just use it as an auxiliary algorithm, which is also commonly done. For example, here with potential fields. In this example, you can see a potential field, and in the middle is a goal, and there are some obstacles with repulsive forces, so these ones. And from these two different starting points here, you can see that, the one here gets stuck between the obstacles, and you could use simulated annealing to escape those local minima. So it's also common to use it as an auxiliary tool. But yeah, potential fields are usually just used for educational purposes because in practice they have too many problems. So we will look at a pure simulated annealing approach. The paper I've implemented, you can find it here below. I implemented the most simple version here because it's also the easiest to visualize. A solution consists there out of a polyline. So from start to the goal, we just place here, in this case, 3 vertices. We want to avoid the obstacles here and find a path that is as short as possible. So let's look at this in detail. So at first we generate our random solution and we have to choose the number of vertices of our polyline in the beginning. And then our path will be a polyline, so it will be straight lines as shown previously. So now we have to define what is our neighboring solution. And for this we take one vertex and we will compute a random displacement in x and y direction and just move this vertex slightly or even by a large amount. And we also need a cost function, and this cost function is defined by adding the path length to the obstacle intersection, so the length of the path which is within an obstacle. But as we really don't want to have any collisions on our path, we multiply the obstacle intersection by a factor. So then in the beginning, at a high temperature, our algorithm will optimize for having no collisions. And later on, when the temperature is lower, it will focus more on the path length, as the path length will not make such a big difference in the beginning. And for computing the neighboring solutions, this paper has proposed a specific way to do this. First of all, we have a random step size. So that's basically this part of the equation. Here, the random value between -1 and 1. We multiply it with a step factor, which will decide how large our steps are in general. But we sum several of these values. So we have a number of summed random values, ti here. So we will sum a lot of random values. And then we will add this, we will compute this twice for x and y direction. And this will be then our displacement. And now the special part here is that if we accept our displacement in x and y direction for our vertex, we decrease the number of some random values for our vertex I. And otherwise we increase it, so when we accept it. Basically this means if we accept the displacement, then we will generally take larger steps, but this will be a normal distribution, so we still focus more on shorter steps. But if we keep declining our displacements, then we will start making larger and larger steps. So this way the algorithm adapts to the current situation. But also in the end, if the values are pretty high, as it's a normal distribution, we will still have a focus around 0. So we will still also make a lot of small steps. Yes, so that's basically it. And now we can switch to the algorithm in action. Here you can see a map. Unfortunately, this map is not from another planet, as I don't have a rover on Mars or somewhere, so I couldn't generate one, but maybe in the future. This map is just from University of Würzburg. So we have 2 corridors in here, and our goal is to drive from the top here to the bottom. And as humans, we can quickly see that a good solution would be to drive down this corridor and then straight down this corridor to get to our solution. As an initial solution, I decided to pick a straight line and add our 5 vertices on this line, and our path is then the polyline here. So let's see what happens if I start the algorithm. It actually doesn't show every single iteration. It always skips a couple of them. So initially we just move randomly a bit, but now we already can see something interesting. So if I pause for a moment, if you take a look at these ones here, these vertices, and compare it with this one, you will realize that they move less. So here they don't move that much, just a couple of times, where this one keeps moving all the time. And as the algorithm has this addition to count, to increase a number of some variables when we decline a state, a neighboring state, the number of some random variables here for these ones will grow. So the normal distribution here also grows from time to time. So we consider points that are further and further away for other solutions. So here we can see that finally we considered a point that could help us overcome a local minimum, and we already see the solution is a lot better here. We still drive through the wall here, but when we continue here, we will from time to time climb here the corridor up, and now we already have a solution that has no collisions anymore. And now the algorithm starts to consider the overall path length more. But here's also a small weak point. It is here you could decrease the temperature quite a bit faster. But at the end we will find a rather good solution. By the way, this algorithm does not run in real time, so it actually runs a lot faster than this. So now we converged and we don't find any better solutions. We can see here another rather large problem, as we initially did not consider the robot size in our cost function. So when we have a look here, we want to minimize the path lengths. So so the algorithm optimized here to drive as close as possible to the wall without colliding. But obviously in practice, we would collide here. So as an extension, one should actually add some value to the cost function to make up for the robot size. And there could be a couple of more small optimizations, but yeah, we found a pretty good solution with a basic simulated annealing algorithm. So to conclude the video, we have seen how simulated annealing works as a concept in a general way, and we have applied it on the problem of path planning, and now we have seen what are possible future steps that should be taken before using this in practice. Thank you for watching.